Tomorrow we have another happy event. First part will be during your scheduled discussion class. Second part, 7 p.m. in the evening as usual. Same location. I'll not be able to meet my office period scheduled after lecture class today because I had a late appointment to see my physician, who called me an hour ago and said he's got to go out of town at 3 o'clock, so I have to go earlier. So I have to be there at 2:15, which means when we finish, then I pretty much got to take off to go there. Now, more on atomic size. In particular, the size of the atom in the bound state, to which I will refer as covalent radius rather than atomic radius. As we mentioned yesterday, since the bound state is ever so obvious the state in which most atoms exist, at least under normal laboratory conditions, it must be true that the main driving force from an atomic standpoint of bond formation is an increase in stability of valence electrons. And the only way electrons can get more stable when they belong to an atom is to get closer to the nucleus. So this is screaming at us. For any atom, its covalent radius will always be shorter than its atomic radius, the size of the atom when it's in the unbound or free state. With that, we talked in brief yesterday about the size of a nitrogen atom. For a gas phase nitrogen atom all by itself versus the size of a nitrogen atom in the nitrogen molecule. Well, you know from Lewis structure analysis, the stability and integrity of the nitrogen molecule is maintained by a triple bond. So you can well expect the covalent radius of nitrogen in the nitrogen molecule is a good deal shorter than the atomic radius for the free nitrogen atom. Now, more on the mystery of atomic size. Because in the nitrogen molecule, you don't have just one size for the nitrogen atom. You have its covalent radius. How is that defined? You take the internuclear separation, the bond distance, divided by 2. That's the covalent radius for nitrogen, in this case in the nitrogen molecule. But what about the size of the nitrogen atom? In the vicinity of space for the nitrogen molecule, which is directed away from the bond, like this way, to the exterior surface of the nitrogen molecule, which again looks rather like an egg. Here's a nucleus, here's a nucleus, and if you could see a nitrogen molecule, what would it look like? The two spherical nitrogen atoms merge to the extent of making the strongest possible bond interaction between the two atoms to give us the nitrogen molecule. Well, clearly, the distance between these two nuclei divided by 2, which is the covalent radius, is a whole lot shorter than the distance from any nucleus to the exterior surface of the nitrogen molecule itself. Well, how do we refer to this other size property of the nitrogen atom and the nitrogen molecule? Called van der Waals radius, which I expect you heard about in 2045. Well, this tells us more about why talking about the size of an atom is rather a mysterious thing, particularly when it's in the bound state. If, for example, we extend this consideration to the hydrazine molecule, perhaps you've heard of hydrazine. Condensed formula is N2H4. It's a commonly used rocket fuel ingredient Cape Canaveral folks deal with this stuff. Highly reactive with strong oxidizers. A mixture of this with liquid oxygen or with hydrogen peroxide, whew, that's a real high energy mixture. Lewis structure. Well, if I'm going to talk about the covalent radius for nitrogen in the hydrazine molecule, how's this going to compare to the covalent radius of nitrogen in the nitrogen molecule? There's going to be a longer radius? Yeah. If nothing else, the Lewis structure analysis tells us between these N atoms we now have a single bond. A single bond is longer and weaker than a double bond, which in turn is longer and weaker than a triple bond. So this is the shortest, strongest bond interaction of nitrogen atoms with each other. However, not only can I observe the size of the nitrogen atom in this, the hydrazine molecule, by taking this internuclear separation and dividing it by 2, I can take the distance between a nitrogen atom and a nucleus and a hydrogen atom nucleus. Well, how am I going to talk about the size of the nitrogen atom, nitrogen to hydrogen, for this NH bond? That's difficult. I mean, if I just connect the nuclei and I divide this by 2, I know that hydrogen is a good deal smaller than nitrogen. So that's not really a fair assessment of the size of nitrogen, because this would correspond to hydrogen being too big and nitrogen being too small. But what else can I do? If I look at the size of a nitrogen atom in the NCl3 molecule, how does a chlorine atom size-wise compare to nitrogen? Which one's bigger, chlorine or nitrogen? Remember when we go from period to period, we observe for A family atoms a significant increase in size? Chlorine's in period 3, nitrogen in period 2. So we should well expect chlorine to be a good deal larger than nitrogen. But when I look at a nitrogen molecule with an electron microscope, I don't see where the nitrogen electron cloud stops and the chlorine electron cloud begins. There's no definition of where the nitrogen covalent radius terminates or where the chlorine covalent radius terminates. So what can I do? I'll take the internuclear separation and divide by 2. Well, any simple consideration will cause us to recognize that if I observe the size of nitrogen in this molecule based on the NCl bond length, because that's all I got here, versus NH bond length, if I do this, for example, for ammonia, I got a problem. Clearly the nitrogen atom is going to be observed to be smaller here than it is here, which gives us one more illustration of why trying to assess the size of nitrogen in the bound state, or any atom in the bound state, is really a difficult task. All you can do is make reasonable estimations. You can't give an absolute value. Now, a couple more questions related to this size stuff. We're going to skip through all the material that you see in the notes, which takes us from this consideration to these questions. That's the stuff we talked about in brief yesterday, and which I have asked you to pay attention to by looking at the video, which I renumbered 000041 on periodic size trends. 23.9, which we did talk about yesterday, if you recall. Based on radial probability, in the notes, there are 4 radial probability graphs labeled A, B, C, D. So based on these radial probability graphs, where shall I expect to see a significant difference in size for scandium, to scandium plus to scandium 2 plus, scandium 2 plus to scandium 3 plus. Between which pair of these scandium-derived species, including scandium itself, between which pair of these species, based on radial probability, should I expect to see the biggest difference in size? We'll look at the radial probability graphs. First A. That's on page 2310. That tells us, as we've already recognized, as you go from period to period, you see a substantial increase in size. In this case, that's reflected by the most probable distance of 1s versus 2s versus 3s versus 4s electrons from the nucleus. Now, when you go to radial probability graph C, take a look at that. These graphs all come from the theoretical folks who study this stuff and do calculations all over the place. Radial probability graph C tells us what kinds of electrons for any atom define its size. By that I mean, if I look at an atom which has in its electron configuration, its total electron configuration, S, P, D, and F electrons, since these are only 4 different types of electrons so far encountered. Which of these electron types will determine the size of the atom? S, P, D, or F? This says S, because most probable distance here for 3s versus 3b versus 3d, most probable distance for 3s electrons greater than that for 3p, greater than that for 3d. So when I am concerned with the size of a species, of an atom in a species, I pay attention to the total electron configuration for this atom and look for the highest n value electrons. Those are the ones which will determine size for the atom. And now when I go to radial probability graph D, I'm seeing the great difference in most probable distance for 4s versus 3d electrons. Why is that of concern for a species like scandium? Well, what distinguishes the chemistry for these transition metals, first one of which is scandium, from the other metals? What distinguishes their chemistry from the other elements, from the other metals, is the fact that they have a mixed bag of valence electrons, S and D. The first row transition elements, scandium on down through copper, because zinc is really not transition, have valence S and D electrons, 4s and 3d. The second row transition metals, that's yttrium down through silver, have again a mixed bag of valence electrons, 5s and 4d. And then when we get to the third row, shown at least for what we see on the board, hafnium on down through gold, HF down to the symbol for gold, AU. Now 6s and 5d valence electrons. Well, radial probability graph D, the top of page 2313, is telling us that we find a big difference in most probable distance from the nucleus for s electrons in an energy level compared to d electrons, which are also valence, but in the next lower energy level. 4s versus 3d, 5s versus 4d, 6s versus 5d. So, with this information, we can answer this question. Here's scandium. The size-defining electrons of this configuration are 4s. Here's scandium plus. I still got a 4s electron. So based on radial probability, I don't expect to see too much difference in size between these two. But I also know, keep in mind, when an atom loses an electron, you know for a fact that the single plus cation, that's what you got when an atom loses an electron, compares how size-wise to the paired atom? It's got to be smaller. Usually a good deal smaller. After all, when you have an atom which has a balance of electrons to protons, same number, and you lose an electron, you've increased the average nuclear attraction for the remaining electrons. And you reduce the degree of electron-electron repulsion because you got fewer electrons. Nothing fancy about that. Which guarantees that SC plus is smaller than this. But based on radial probability, we don't expect to see a whole lot of difference. And keep in mind, scandium's number 21. So you got 21 electrons, 21 protons for the atom, but 21 protons, 20 electrons for SC single plus. So you haven't really changed the ratio of electrons to electrons a whole lot, nor have you increased the average nuclear attraction a whole lot. It went from 21 to 21 for the atom to 21 to 20 for the ion. But when we go to scandium double plus, now all the 4s electrons are gone. Now we have a species which no longer has any electron density in energy level number 4, specifically 4s, because we recognize of the different types of electrons which can be part of a configuration. It's the highest n value s electrons which determine size. Well, when I go then to SC double plus, which electrons? Based on what we've said, which electrons for SC double plus determine its size?
3s.
3s. They're part of that argon configuration. They'll have the largest MPD. But if, for example, you go back to radial probability graph A, big difference in MPD 3s versus MPD 4s. So here's where we see the big gap, right here. Big size gap. 2310. 2310 is asking you to focus on stuff that you all talked about in 2045. Let's take a collection of atoms, A family, and ions derived from A family atoms, and see if we can line them up with respect to relative size. Starting with smallest, winding up at the end with the largest. What are the considerations? When an atom loses an electron to become a cation, it gets smaller, in some cases a good deal smaller. Opposite, an atom gains an electron to become an anion. Well, now you have reduced the ratio of protons to electrons. It's now less than 1 to 1. So the average nuclear attraction is now smaller than for the parent atom. And you've increased the number of electrons in the cloud. So for the atom, the degree of electron-electron repulsion is increased. Consequence, the atom has got to be larger. The anion's got to be larger than its parent atom. Now, based on data which I've seen, the data suggests that for all the atoms in the same period, lithium, beryllium, boron, on down through neon, if you make a cation out of any one of those atoms, you'll wind up with a species which is smaller than any atom in the period. Could that be wrong? Yes. But the data which I've seen suggests that as a generalization. Other side of the fence, if you take all the atoms in the period and take any one of those atoms and give it an electron and turn it into an anion, Data suggests that that anion will be larger than any atom in the period. So any cation derived will be smaller than any of the atoms, and any anion derived will be larger than any of the atoms. And we already know how to compare the size of the atoms based on periodic size trends we've already considered. As we go left to right, the atoms are getting progressively smaller. So, with that, when I look at the species listed in 2310, you look at them. Which one is the smallest? What do you say? You think the smallest one would be one of the positively charged species? All right, we'll start with that. Now you got 1, 2, 3, 4, 5 positively charged species in here. Which one is the smallest?
4+.
I heard lithium 3+ and I heard carbon 4+. Well, it's one of those. Which one is it? Lithium 3+. Why?
There's no electrons. There's no electrons.
Lithium 3+ is a nucleus. So that's the smallest. Now let's jump to the opposite extreme. Of the species listed, which is the largest?
Scandium or SB.
What is SB? Antimony. Now, you look at these formulas. I'm pretty sure you can line them up correctly. I'll read the order, starting with Li3+. Next, carbon 4+, Si4+, Mg2+, Na+, then neon, chlorine, aluminum, the phosphide ion, that's P3-, and this, the antimonide ion. I don't care about the name, just call it Sb3-. Any questions about this order? Last, 2312. No, wait. Next, 2311. Pardon me. Atom sodium, single charge magnesium ion, and single charge sodium ion. Here's the size order. Does that size order seem correct to you? If so, why? What can you say about Na and Mg+? Why can you say Na is bigger than Mg+?
They have the same amount of electrons, but Mg has no protons.
That's right. They're isoelectronic species. They both have a single 3s valence electron. But Mg+ has got 12 protons pulling on that configuration. Sodium only 11. But when we go to Na+, now we're looking at a species which no longer has any energy level number 3 electrons. So based on what we've said, it already follows that Na+ has got to be smaller. Na+ is neon configuration. And as we know, as an isolated species, Na+ is smaller than neon. Because Na+ and Ne are isoelectronic species. But just as we decided between Na and Mg single plus, Na+ and Ne, the neon atom, are isoelectronic, but for Na+, you got 11 protons pulling on that configuration versus only 10 for Ne. Enough said. Last question 2312. Data which I've seen provide indication that the hydride ion, H-, the simplest anion, is a good deal larger than the lithium atom. Do you find that unusual? Now notice, from a configuration standpoint, this is 1s2. This is 1s2, 2s1. So based on this radial probability stuff, you would expect this to be larger. The data suggests this is a good deal larger. Could you offer an explanation?
The hydrogen atom only has one proton.
Keep going.
Positive charge density is just really small compared to lithium, who has 3 protons.
Well, you're getting there.
And it has the electron repulsion is kind of allowed to be larger.
Well, when I go from H to H minus, what have I done to the proton to electron ratio?
2 to 1.
I cut it in half, didn't I? It's 1 to 1 for the atom, but 1 to 2 for the ion. Now I have reduced the effective nuclear attraction on the electrons considerably and magnified the degree of electron-electron repulsion considerably. There is no species which has a smaller proton to electron ratio than this thing, which accounts for why this is a big species. Question. What do you think about the reducer strength of this? Remember what a reducer is? I hope so. What do you think about the reducer strength of hydride ion? You think it's a good reducer? Ooh, that's a beauty. You want to give something electrons, that'll do the job in most cases. How many of you are going to organic chemistry? Next term or in the future? Okay. Hey. You're going to find out that a whole lot of organic species that need to be produced by reduction are in fact produced by hydride reduction. Common sort of method. One last consideration about size, since I wrote on the board yesterday the remark that atomic size is really a can of worms. K versus Br minus. Now, the statement we made a moment ago. Remember the statement? If I look at all the atoms in a period, and I turn any atom into an anion, I can expect that anion to be larger than any of the atoms in the period. But there are loopholes in this statement. One of the things you have to be very careful about in science class is a generalization. Because as soon as you come up with a generalization, somebody who's got information at his or her fingertips is going to come up with an exception to this generalization. When we go to period 4, where we find potassium and bromine, do you think we can well expect to see a pretty good difference in size between K atom and Br atom? These atoms, K and Br. Not the anion for a moment. These atoms. Look at how many size differentials I'll go across before I get all the way to bromine. Look at all the atoms intermediate between K and Br. If I look at size data, I will see that the K atom is a whole lot larger than the Br atom. But now when I add an electron to this and turn it into this, now I have observed a substantial increase in size. So what counts more? The increase in size by adding an electron to this, or the size trend? How can I find out? The answer is I can't. Now I can make measurements to get a pretty good idea of the size of K. What measurement would you make? I ask this because you talked about this kind of stuff in 2045. Based on your knowledge of chemistry from 2045, whatever that may be. What studies did you engage in that would allow you to get at the size of an atom?
Electronegativity. No?
Not at all. I'll draw a picture on the board, see if it jogs your memory. Does this help? What's this remind you about? What did I draw a picture of? What is that? A cube. When did you pay attention to or have to think about cubes in 2045? Solid state structure, didn't you? Unit cells. Okay? So I can take a chunk of potassium and study it by X-ray so I know what its unit cell is. Face-centered cubic, body-centered cubic, whatever it might be. And then I can make some measurements on potassium, a sample of potassium, to find out the internuclear separation between potassium atoms in the potassium unit cell. This gives me a good idea of what the K atom is size-wise. But how am I going to get a good handle on the size of Br minus? Or any anion for that matter? What am I going to do? I'll tell you what's usually done. We take an ionic solid which contains the anion in question and do X-ray studies on it. Well, yeah, that's good, that's good. But what if I have available these three ionic solids? What do? Do you bet that if I observe the size of the bromide ion in this lattice, I'm going to come up with a shorter value, a shorter radius than I will if I observe the size of the bromide ion in this lattice? Or this lattice? Because K plus is bigger than Na plus, and Na plus is bigger than Li plus. So when I'm looking at this information that I got from X-ray spectroscopic observation of an ionic lattice, do I see a distinct exact point where the size of the sodium ion terminates and the size of the bromide ion begins? So I wind up with having to make an approximation. Best I can do. More on why this size stuff is very difficult to deal with. In any case, we've said enough about atomic size so that at least we know now how to compare sizes. We can compare sizes relatively speaking. And that's good enough for the game we want to learn how to play regarding rationalization of strengths of Bronsted-Lowry acids bases. Now let's take a look at a couple of other fundamental considerations which will also relate to this issue. In the notes as you examine such, you will see next is considered electron affinity. When I rewrite these notes, I won't even put electron affinity in there, because electron affinity has really no bearing on the size of an atom in the bound state. And we're concerned with atomic size in the bound states, because we're going to talk about molecules and how strong they behave as Bronsted acids or bases, not isolated individual atoms. So we'll go to electronegativity. You know trends in electronegativity. You did this in 2045. If this is our periodic table, and this is fluorine, because you won't see an electronegativity trend as yet, which includes the inert gases. Because electronegativity is a measure of the ability of the bound atom to attract valence electron density to itself. And the noble gas atoms rarely form bonds. So, the standard electronegativity periodic pattern is established by considering the electronegativities of cesium through and to fluorine. We again discount francium because of its strongly radioactive nature. All right? Now, up here, we got lithium. And over here, well, let's put down, let's stop at iodine because acetine is radioactive. As I go from cesium to lithium, how do electronegativities change? Increase, decrease, stay the same. Increase. Increase substantially or slightly. Remember, these are all atoms in the same chemical family. Do they show comparable electronegativities or large differences in electronegativities? Comparable. So En along this arrow increases, but not greatly or significantly. Now let's go lithium to fluorine. Well, we know fantastic fluorine is number one in the electronegativity game. So here, En increases greatly. En lithium 1.0, fluorine 4.0. So this gives me a handle on electronegativities. Now, let's take this property of atoms, known as electronegativity, and see if we can expand upon it and call it orbital electronegativity, symbolized by OEN. We're on page 23AT. O is orbital. There's a nitrogen-hydrogen molecule which is rather similar to hydrazine. Let's put hydrazine back. And since these are each molecules composed strictly of N and H atoms, let's put the one on the board with which I am sure we are most familiar. Ammonia. The question is, which of these is the strongest base? Bronsted-Lowry base. I do this because we've already said our main intent in Chapter 23 is to establish a basis for rationalization of Bronsted-Lowry acid-base strength. So what we're going to do now is to show how orbital electronegativity relates to this. And then we're going to ask, which is strongest Bl acid? These three molecules. Now we'll wrestle with the acid issue secondly, because our studies of Bronsted-Lowry acid-base chemistry has shown us that in water solution, ammonia behaves which way? Base. But we haven't found it yet to behave as an acid, have we? No. So at the minimum, do you think it's a fair statement that ammonia, if it is a Bronsted acid, because it has to be, it's got hydrogen in its composition, so under appropriate circumstances it can lose H as H+, that at minimum, ammonia as a Bronsted acid is a very weak Bronsted acid. Fair enough? Okay. So back to the base business. We know when these things behave as a Bronsted base, they do so by collecting H+, right? Isn't that how a Bronsted base operates? So here's H+. If you are in a water solution that contains this and this and this, and the molarities of these are all the same, on which of these Bronsted bases will you, the H+, land? Well, of course, you're going to land on that one of these, which is the strongest Bronsted base. So which one do you expect to be the strongest Bronsted base? Now notice you can't answer this by just talking about the electronegativity of nitrogen, because nitrogen is the atom in each of these which contains the non-bonding pair.
I think it's the top one.
Well, I don't know what you mean when you say top one.
N2H+.
So let's call it A, B, C. Okay?
I think
You want to vote for A.
A. Yeah.
Tell me why you want to vote for A.
Well, I don't think it's ammonia because it can only pick up one.
Wait a minute, we're not talking about how many H pluses you can get. Base strength doesn't depend on how many you can get. It depends on how strongly you get. We're talking about adding one H plus. A, B, C. Well, the answer to the question depends upon the effectiveness of each of these regarding ability to share electron density, non-bonding electron density with H+. Fair enough? Okay. You had a comment? All right, okay. You want to think about it, that's good. Now remember how this is defined. Orbital electronegativity. Fair enough? So I want you to look at these nitrogen atoms. Tell me how they're hybridized. A, N is, B, N is, C, N is. You got to play this game. You did this in 2045. That doesn't mean you know how to play it. A, N is sp3. B, N is C, N is
sp2.
You remember how to get hybridization when you have a Lewis picture before you? Statement. Look at the notes. Page 2320. Summary of rules for drawing Lewis structures. Page 2321. 2322. The same table of information I have available for your use in the 2045 laboratory manual when you do the Tinker Toy experiment. Page 2323. Look at page 2323. That sums up all the stuff on playing the hybridization game along with determination of molecular geometry. It's all there. So if you need to review this, it's all here. Now let's go back to the pictures on the board. Regarding hybridization, pick an atom whose hybridization you wish to determine. And then do what? Did you learn that hybridization applies strictly and exclusively to sigma electrons? So when you're looking at a Lewis structure, you have to be able to count the number of sigma electron pairs an atom has in its valence environment. Number of sigma electron pairs. At each and every covalent bond site, how many sigma electron pairs do you find? One. And non-bonding pairs are sigma or not? They are sigma. So, nitrogen. sigma pair, sigma pair, sigma pair, sigma pair. That's 4 sigma pairs, right? So I'm going to pick the hybridization scheme. What hybridization schemes are you familiar with? Let's write them down. SP, SP2, SP3. And now we've exhausted all the blends we can make of S and P orbitals from a given energy level. Because at any given energy level, you only got 1 s orbital, and you got 3 p orbitals from the p sublevel in that energy level. So then we go to sp3d. Then we go to sp3d2. Up to 6 sigma pairs. Can we go past this? How many hybridization schemes can you make for the orbitals from an energy level like energy level number 3, where you have d orbitals? Now we can go to sp3d3, 7 sigma pairs. sp3d4, 8 sigma pairs. sp3d5, and now you've exhausted all the d orbitals, and you have the opportunity to accommodate 9 sigma pairs. Because this hybridization stuff is just a game. So let's play the game to its maximum extent. Now, will you ever see hybridization schemes that include f orbitals? Yes or no? Have you seen any hybridization scheme? No, you haven't. Why not?
Because they're hard.
No. F electrons and f orbitals are, practically speaking, never part of the valence environment. Remember, we're concerned with valence electrons and how they behave. Well, if f electrons and f orbitals are hardly ever part of the valence environment, they're not going to be part of the hybridization game. Because this is a game we're using to explain valence properties of species, bonding properties. All right? Now then, back to this. sp2, only one of these pairs is sigma, the other one is pi. So for either of the nitrogen atoms, 1, 2, 3 sigma pairs, sp2. Because this is a blend of 3 orbitals. So it gives you a parking place for 3 sigma pairs. Ammonia, 1, 2, 3, 4. Just like here, 1, 2, 3, 4. All right? Now then, back to this base business. Let's immediately make a distinction between the base strength of C versus the base strength of A and B. Based on this. Based on orbital electronegativity. Statement. If you are an electron and you're going to move into an energy level, and when you approach this energy level, you see in front of you s orbital, empty. P sublevel, 3 p orbitals, all empty. D sublevel, 5 orbitals, all empty. You're in a particular energy level. So you are looking at S, P, D, empty valence orbitals, all in the same energy level. Tell me, Mr. or Ms. Electron, in which of these orbitals do you take residence? S, P, or D, or is it a toss-up? In which of these orbitals do you take residence?
S.
S. Why? Well, it must be true that the s orbital is the lowest energy, the most stable. Why? You remember this business of penetration? You remember when we talked about ionization of beryllium versus boron? More protons in the nucleus of boron, but it's still easier to ionize, because for boron you're taking away a p electron, and that's not nearly as tightly held as an s electron, because these s electrons, even though they have the larger MPD and define the size of boron, like they also define the size of beryllium, on a time average basis, not only are they farther from the nucleus, they're also closer to the nucleus, these dirty little buggers, because they're waves. And when they're closer to the nucleus, they're more stable. And that closer to the nucleus property is referred to by the theoretical people as penetration ability of s electrons, which exceeds that for p or d or f electrons, with all the electrons in question being in the same energy level. How about that? So we now know that atomic orbitals will line up. S most stable, then P, then D. Well, then let's apply this to a hybrid orbital. Tell me, if you as an electron can take residence in an sp2 hybrid versus an sp3 hybrid, where are you going to go?
SPC.
Why?
Because there's more like S character.
More S character. That's right. This thing is 33 1/3% S character and about 67% P character. But this is only 25% S character, right? Because there's 4 orbitals total, only one of which is S. So 25% S character, 75% P character. All right? If you're going to move into one of these, please recognize you're going in here. That's 50% S character. And this is the last one you'd go into, because this is least in S character. All right? So for hybrid orbitals derived from orbitals from the same energy level, the hybrid orbital of greatest orbital electronegativity is the one with the highest percentage S character. That's this, of all these. That's what this game is all about. So tell me, these sp2 nitrogens, which have non-bonding pairs, compared to these sp3 nitrogens, which of these N atoms stabilizes its non-bonding electron density more effectively? See? You betcha, because it's sp2, which makes these non-bonding pairs least likely to be shared with H+. These non-bonding pairs are stabilized to the greatest extent by these nitrogen atoms because of their sp2 hybridization. Let's extend that. Here's an NN bond. Here's an NN bond. Of course, this is a double bond, this is a single bond. Can you now see why a double bond is stronger than a single bond? Because the double bonding electron density is stabilized by an sp2 atom versus an sp3 atom. Hey, greater S character for the hybrid of these atoms stabilize the bonding electron density more effectively, makes the bonding electrons more stable. And here we're talking about stabilizing these, because these are the electrons which have to be used to make a bond with H+. Well, these are stabilized more effectively than these. These non-bonding pairs are more reactive. They more readily react with H+. So we know now that trying to decide which of these is the strongest Bronsted base, this one's out. Now let's decide between these two. And we're going to decide on the basis of another extension of this electronegativity idea. Electronegativity is a really powerful idea. I'm showing you now some of the things you can do with it, and you're going to do these things all the time in organic class. Let's be more brutal about this. Let's tell you that if H+ is going to go between these two, here's the winner. Why is this the winner? These are each sp3 nitrogens. But this is a stronger base than this. Why?
Because you have a bond pair between the nitrogen, whereas B doesn't. So
Say again?
because A has a bonding pair between the two nitrogens, where B doesn't, so that makes P.
Well, you're recognizing that the only difference between these is here I have an NN single bond, whereas here I have only NH single bonds. Here I have two NH single bonds and an NN bond, right? So the difference in base strengths of these two molecules has got to have something to do with this bond versus one of these. Okay, so far? And the answer is determined by an extension of this electronegativity property called induction. Shorthand spelling for induction. Save some of my favorite weapon. What does this word mean, induce? If you induce something to happen, what's that mean?
Force it.
Well, I don't know about forcing it, but you've made it more favorable. Okay? Now tell me, H versus N. Which atom is of greater electronegativity? N. So, by induction, will this atom cause stabilization of this non-bonding pair more effectively or less effectively than this atom exerts stabilization on this non-bonding pair? By induction. This atom is more electronegative than this atom, right? So this atom exerts a stabilizing effect on this non-bonding pair because the electronegativity of this atom, which exceeds that of this atom, tends to take this electron density and draw it toward this atom. Just like this is drawn toward this atom. But this electron density stabilization by induction is greater for this molecule than it is here because N is more electronegative than H. Interesting, isn't it? Now we're going to do more of this as we proceed with chapter 23. So if this issue right now is causing you some confusion, it'll clear up. Don't worry about it. Now let's look at the acid part. If you have followed what we've said about orbital electronegativity, then at a glance you can see why of these three molecules, this is the strongest acid. What is that? Well, let's make a picture illustrative of what you have after each one of these things behaves as an acid. Okay? These H's are all identical. So let's lose this one as H+. All right? That puts a minus charge on this nitrogen. Let's lose this as H+. That puts a minus charge on this nitrogen. Let's lose one of these as H+, putting a minus charge on nitrogen. Each case we got a minus charge on nitrogen. Which of these N atoms stabilizes that minus charge most effectively? C. Why? Because the N atom is sp2 hybridized, and I stabilize electron density more effectively with a hybrid orbital, the greater is its S character, right? How about that? That's the game. And it's a powerful game. And it's not a difficult game at all to play. It's not hard to recognize that an sp2 hybrid is greater in S character than sp3. So what we're doing is paying attention to, in this case, this extension of the concept of electronegativity into orbital electronegativity to find out how a hybrid orbital stabilizes electron density. No more, no less. That's all there is to it. Now then, let's go to the very first part of the game we're now going to learn how to play. That game being establishing a basis for rationalizing strengths of Bronsted-Lowry acids and bases. I got two molecules. Hypothetical, HX and HZ. I want to see if I can explain which is the stronger acid. Given that an atom of X is bigger than an atom of Z, but the electronegativities of X and Z are practically speaking the same. Let's do this, because no two atoms have identical electronegativities. Which molecule is the stronger acid?
Maybe HX.
Maybe.
Well,
Not maybe.
it has more S orbitals.
More S orbitals.
Not necessarily.
HX because it has a better ratio of s orbitals to p orbitals?
How do you know that? Did I tell you anything about what atom X really is? All I've told you is that the electronegativity of X and Z are about the same, and that X is a bigger atom than Z. That's all I've told you. And that information is enough to allow you to decide that this is the stronger acid. Why?
It gets rid of the H and becomes X minus. It'll have more, it can spread out the minus charge easier because it's bigger. I don't know how to say that.
There's your directive. Consider stabilization of negative charge density based on charge to size ratio.
X has a lower charge, has a lower positive charge density, so
Whoa. Where's this positive charge density coming in?
from the nucleus.
If this thing loses H plus, I got X minus. If this thing loses H plus, I got Z minus. Now notice I purposely drawn these pictures bigger than these pictures because when we go from a neutral atom to a negative ion, size expansion increases, doesn't it?
So Z minus is a better base, so by the conjugate,
How do I know Z minus is a better base?
because it has more negative, like negativity packed into those small space.
It has a greater negative charge density. Why does it have a greater negative charge density?
It's smaller.
It's smaller. These things have the same electronegativity, so they're going to stabilize negative charge density to the same extent based on electronegativity, right? Because their electronegativity is about the same. So the distinguishing feature between these two is charge to size ratio. If I have an electron, which is this wave thing, and so it can be all over the place at the same time, and I smear my electron on the surface of a basketball, and I have another electron and I smear it on the surface of a baseball. Basketball, baseball. Each has one electron smeared on its surface. Where do I have the negative charge more concentrated? On the baseball, because it's smaller. So that's the stronger base because I've got a higher negative charge density. Well, here's the opposite effect. When I smear the negative charge density on the larger sphere with the electronegativities being equal, that makes this the weaker base. And once I know this is the weaker base, then I know this is the stronger acid. Enough said. Now let's play this game one more time for today. Same size. But the electronegativity of X exceeds that of Y. There's the anions. That's what I get when HX and HY each do their Bronsted acid thing. Which of these bases is more stable? Which of these bases has the smaller negative charge concentration? Which of these bases is derived from the atom of greater electronegativity? This one, right? Because it said X is more electronegative than Y. So here, I can't really size up effective negative charge density based on charge to size ratio because these damn things are each -1 and they have the same size. So I got to look at something else. The something else I looked at is called electronegativity. The electronegativity of X is greater than that of Y, which means based on electronegativity, this negative charge density is stabilized to a Greater extent than this electronegativity. That makes this the more stable, less reactive base, or the more reactive base. Which is it? Less reactive, more stable base, because the negative charge density is stabilized to a greater extent, because this is derived from the atom of greater electronegativity, guarantees that this is again the stronger acid. Absolutely. And that's our first look at how we play this game of deciding on acid-base strength. Pick it up from this point next time. Have fun tomorrow.